Alright, so on day one we talked about how repeated multiplication can be represented with exponents, and that is going to be our focus for today's lesson. So whole number exponents tell you how many times to repeat that multiplication of a base by itself. So there's just a couple examples here. Things like this are actually commonly done incorrectly, even though they're not that complicated, because when we see 3 squared, sometimes if we're not careful we think 3 times 2. So we've just got to remember that the base is what we're multiplying, and this is just telling us how many times. So it's actually not 6, it's equal to 9. If you have a parentheses, whatever is in the parentheses, the whole thing, is what gets repeatedly multiplied. Right? If you have something like this example over here that has a negative out front, your order of operations, exponents, comes before a multiplication of essentially a -1. So that negative just stays out front. It does not get multiplied repeatedly. It has to be in parentheses for the negative sign to be part of what is repeatedly multiplied. Alright, so let's just dive into some examples here. Again, they've given you a couple to start with. And I know it'll seem a bit tedious at first to write these out, but I promise that it will help the rules and shortcuts we use make more sense. So let's take a look at A. It says 8 to the third times 8 to the fifth, and we're going to write it out first. So our first group is 8 being multiplied 3 times, and then we're multiplying that by a base of 8 being multiplied 5 times. And so we only have one base throughout this problem, which of course is an 8. And the number of times that this occurs in total is 1, 2, 3, 4, 5, 6, 7, 8 times. Happens to be the same number. Alright, for problem B, we have 2 powers going on here, so let's be careful with this. We're going to do like they do above, where the first thing that they do is expand what's inside, and then we worry about the power on the outside. So on the inside of this function we have 2 being multiplied 3 times, and we're raising that to a power of 5. So we're really going to have that parentheses with 3 2's inside get multiplied 5 times. And I did not do a very good job of spacing that out, but we'll have 3 2's, 3 2's, 3 2's, 3 2's, 3 2's. So altogether we have 5 groups of 3 2's being multiplied, which means we have 15 2's being multiplied altogether. Alright, so don't be afraid of fractions. You literally just repeatedly multiply, again, whatever's on the inside. So here we have 1 over 7 being multiplied 3 times. And we like multiplying fractions because when we do this, we just multiply the top, multiply the bottom. But they do want you to keep things with your bases in the directions. It says show the base and exponents, so you don't have to actually simplify. So I'm going to put 1 cubed over 7 cubed, since both of them have the base multiplied 3 times. Okay, so now we're getting to part D, and this one is one where we have more than one base, and it's kind of in a fraction setup as well. So first I'm just going to expand everything. So I have a group with a base of 3 multiplied 4 times, and I'm multiplying that by a group where it has a base of 4 multiplied 6 times. And I'm going to use another color for that. Let's do just slightly different. Alright. And on the bottom we have 7 3's getting multiplied. Oh boy. And they're getting multiplied by a base of 4 being multiplied 5 times. Alright. So just as a quick side note, if you guys remember, if we ever have something like 2 over 2, that actually is just equal to 1. Or a number divided by itself basically just gives us a 1. They kind of undo each other. So when you have these big fractions, what you're trying to do is pair up your bases that you can cancel out. So for instance, this 3 cancels out with this one, and this one goes with that one, and this one cancels out this one, and this one cancels out this one. And so we've now canceled out 4 3's from the top and the bottom, and it's leaving us with these 3 remaining ones in the denominator. Then I'm going to do the same thing with 4's. A 4 over 4 would just give me a 1, and when we multiply by 1, that didn't do anything. So that's why it's called canceling out. Okay, and I just cross as I go, and I'm just left with this 4 on the top. So for this particular problem, we're left with 1 base of 4 in the numerator, and we're left with 3 base of 3's, so I'm just going to write that as 3 to the third power in the denominator. Alright, so we're now turning to page 7, which is basically a bunch of practice problems. So what I'm going to have you all do is I'm going to have you pause the video here in just a second, and you're going to try them in groups of 3 to 4 before I actually show you the answers. So why don't you go ahead and pause the video here, and I want you to try doing A, B, and C before unpausing the video. Alright, so how did you do? For the first one, we should have gotten 5 to the power of 10. For B, we should have gotten 7 to the power of 10. And then for C, you should have gotten 2 to the power of 9. Alright, so again, pause the video, and now I would like for you guys to try D, E, and F, big scary fraction ones. So go ahead and pause the video now, and then give those a shot. Alright, so how'd you do? On D, we hopefully got just a single 8 on the numerator and a base of 6 to the power of 3 in the denominator. Everything else was paired up and thus canceled out and is no longer part of our answer. Alright, so let's take a look at the bottom half of the page. So again, these are just more practice problems. So go ahead and take a look at G and H. Alright, so when you do G and H, something interesting should happen. So when we're looking at example G, everything in the denominator completely cancels out. So what happens? What do I write down here if there's nothing left? Well, remember, when we're canceling out these pairs, and by the way, be careful because they kind of did not line them up nicely on this one. But as I cancel out these pairs, remember, that's leaving behind a 1, a times 1. And we don't normally write times 1 because it doesn't really do anything, but just know that it is going to leave you with a 1 in the numerator or denominator if everything completely cancels out. It never leaves you with a 0. That's one of the big misconceptions a lot of students have here. And so whenever I'm dividing something by 1, that doesn't really do anything. So I can just write my final answer for G as 2 times 3 to the 4. Now when I come to H, something similar happens, except this time it's in the top. So now I realize that that means I'm just going to have a 1 left if everything else cancels out. However, unlike this example we just did where the divide by 1 wasn't really necessary in the answer, if you have a 1 in the numerator, that's extra necessary and that has to stay as part of your answer. The reason being, in G we're basically saying like 2 over 1, well that's just 2. Oh my gosh, I can't write. Woo, right? 2 divided by 1 is 2, that's a fact. However, if I have 1 over 2, we definitely cannot say that's just 2. Those are two very different numbers. So it's okay to drop the 1 if it's in the denominator, but do not drop it if it's in the numerator, because that gives us a completely different number than it is without that 1. Alright, time to knock out the rest of this page, give it a go, and then we'll see how you did. Alright, so there's the rest of this page. Let's talk about a couple things I want to make sure you notice. So for I, we got 3 to the 8th, and then for J, we got 6 to the 5th. Now this is one a lot of students miss. For some reason, just having a plain number, and remember that's really to the power of 1 right here, if it doesn't have an exponent written in. Don't freak out when you see that. Just keep doing what you're doing, right? And it just gives us 6 5s in total to multiply by. Alright, for K, we should have had 5 to the 10. For L, we should have had a whole lot of 9s. I hope you're getting tired of writing these out because we're going somewhere with this. That will be a lot less work. But we end up with 12 9s to be exact. And then on the very last one, we end up with 2 groups of 4 4s being multiplied, which give us 8 4s altogether being multiplied. So what we're going to do now is try to find patterns in all of this work you've just done that will allow us to go straight from this problem to the answer, to where you don't have to show all this in-between work. You can And that's always something that I really like about exponents is when you forget one of the rules, you can kind of just expand it out and do it by hand and still get the right answer. So these will just be shortcuts. If we remember them, great. If we don't, just know you can always do what we just did on this page and just expand it out and get your answer that way. All right, so now we're on to page 8, and it's asking us to see if we can figure out any of these patterns. We'll go over these at the end of class today to see where we're at, but I want you guys to come up with your best ideas for each one. So the first one is asking about the rule for when you multiply numbers with exponents. So you have numbers with the same base being multiplied. So back on page 7, an example of this would be all the ones I've done in purple. So like same base being multiplied, what happens with our exponents, right? We started with a 4 and a 6 as the exponent, and we ended up with a 10 as the exponent, because obviously the base doesn't change. This fraction one, we'll get to that one. Let's look at one that's not a fraction. This one right here. So we had a power of 2 and a power of 6 multiplied by the same base of 3's, and we ended up with a power of 8. This one is the tricky one because remember it didn't have an exponent here, but we now know that means it's really to the first. So we had a power of 4 and a power of 1 for our base of 6, and we ended up with a power of 5. So again, just looking at what we're starting with and what we're ending with, do you see a pattern? If so, in words, explain what that pattern is here, and then it's represented in a more mathematical way by one of these options. So circle either A, B, or C, whichever one you think represents what you just said in words. For number 4, it wants you to write a rule for a power raised to a power. So back on page 7, these are all the problems that I've done in green. So for instance, on our very last one, we had a base of 4 raised to a power of 4, and then all of that raised to a power of 2, and we ended up with a power of 8 at the end. Here we had a base of 9 with a power being raised to another power, so again, power to a power. We started with a power of 4, raised that to a power of 3, and we ended up with a power of 12. Interesting. Up here, way back at the beginning, we had a base of 2 raised to a power of 3, and then that power of 3 was raised to another power of 3, and we ended up with a power of 9. And for part B, we had a power of 5 and a power of 2. We ended up with a power of 10. So what pattern do you think is going on that could jump us straight from the problem to the answer if we didn't want to write all this stuff out? So whatever pattern you think that is for a power to a power, write it in words for me right here, and then figure out which of these best exemplifies that pattern. The last pattern they want us to look for is when we're dividing numbers with exponents. All right, so these are the ones in red and orange. They're also pretty obvious. All right, so with these, just look at each base separately. So like in this one, we'll look at the 6's first. We had a power of 4 on top and a power of 7 on the bottom, and we're left with a power of 3 on the bottom. So what can we do with a 7 and a 4 to somehow have a 3, and why is it on the bottom? Okay. And then right here with the base of 8, we had 6 on top, 5 on the bottom, and remember, this really means 8 to the first, so we ended up with a power of 1, and why is it on the top? Looking at some of these others, here we had 2's and 3's, so if we look at a power of 2, a base of 2, it had a power of 3 on top, 2 on the bottom, and we ended up with 2 to the power of 1 on the top. For base of 3, we had 7 on top and 3 on the bottom, and our answer had a power of 4 in the numerator. All right, looking at example H, we had a base of 5 with a power of 3 over a base of 5 with a power of 6, and we ended up with a power of 3 in the denominator. And then we had a power of 2 on top and a power of 4 on the bottom for our base of 3, and we ended up with a power of 2 in the denominator. So what is going on when we're dividing and we have these bases on either side of a fraction sign? How are we getting these answers over here, where maybe we won't one day have to write all this out? So whatever you think that might be, jot it down and see which of these answers or mathematical representations you think best describes your pattern. Okay, so now we're moving on to page 9, and this is where things get a little crazy. So we're going to look at a pattern in this big giant table that's already partially filled out for you, which is super great. And if we look for the pattern in the table, kind of like what we did yesterday, we can see that 10 to 100 to 1,000 to 10,000 to 100,000 to 1,000,000 to 10 million to 100 million, each time we're basically multiplying by one more 10 than the step before, right? So we're just continuing to multiply by 10, which is what they've demonstrated for us here by writing this times 10 in the box. So if the pattern is to multiply by 10 as we go forwards, what would we do to work backwards? Well, it would be the inverse of multiplying by 10, which would be to simply divide by 10. Or if you're thinking about our lesson from yesterday, because I know you are, you could also multiply by 1 over 10, and that would do the same thing, okay? So glad we remembered that. All right, so now we're going to try and work backwards here. So if we're dividing each time we go backwards a step, you think to yourself, well, what's 10 divided by 10? And as we've mentioned earlier, if you have the same number divided by itself, it just gives you a 1. That's all that remains. And then if I divide 1 by 10, now we're going to start getting fractions. They're going to be smaller and smaller numbers. Okay? And this is going to be the same over here. And now we're going to divide by 1 over 10 times itself 2 times, right? Which would be 1 over 100. Okay, and then when we have one more step back, we would be dividing by yet another 10, so times 10 times 10 times 10 in the denominator, and 10 to the third power is simply 1,000. Ooh, horrible 0. Let me try that again. So this table is helping us understand some pretty complicated things about exponents. The first one that's kind of weird is right here when we get to a power of 0. So this is such an odd thing with exponents, but a power of 0 for any base, it could be 11 or -2 or 6 or 1,000,000. If we raise it to a power of 0, it always gives us 1. So every time we're working with exponents, we're talking about some base number and how many times it's been multiplied. So, like for instance, 10 to the 1 means we've multiplied by 10 one time, which is simply 10. 10 squared means we've multiplied by 10 twice, which is 100. So 10 to the 0 would simply mean we haven't multiplied by this base number at all. And so that means we're still stuck at the very, very beginning of every multiple, which is 1. 1 is the common factor of all numbers in our number system, and when we multiply 1 by any of these numbers, it gives us that base that we're looking for. So this is true for any number, not just base 10. So let's come down here and jot something along those lines down. I'm just going to put a power of 0 means we haven't multiplied by the base at all. Haven't multiplied at all. So 0 times. We've multiplied by our base 0 times. And so it's simply 1. Okay, so the next part of the table that's kind of crazy, I know, I hope you're ready, is when we start getting into negative exponents. Now these are pretty scary for a lot of people, but I'm gonna help you out here. So when we have a power of -1 or -2 or -3, look at how this is somehow related to powers of +1, +2, and +3, right? So you should see some similar numbers, like a positive power of 1 gives us 10, and a negative power of 1 gives us 1 over 10. Positive power of 2 gives us 100. Negative power of 2 gives us 1 over 100. And it just continues in this way on and on and on. So a negative exponent basically means that we're working backwards, right? We're undoing our multiplying of the base, which means we're kind of like dividing it, but we're not going to use division. We're sticking to multiplication here. So basically, we are multiplying by the reciprocal, which means we're kind of flipping it, right? So this is really 10 over 1, and we're flipping it to 1 over 10. And then 100 over 1 is getting flipped to 1 over 100, so on and so forth. Okay, so let's come down here and jot that down. So a negative exponent means we're looking at that reciprocal, that word from yesterday that we talked about, which basically means you're flipping it. I can't write anymore. Flip which side your base is on. So the flipping can go either way. We'll get into more complicated ones tomorrow. Today they'll be pretty straightforward. So we finally made it to the last page of notes. Hurrah, page 10. And these are only working with negative exponents. And so what you'll see for each of the examples is whatever base we start with, right, we're going to find its reciprocal, and that changes the negative exponent to a positive one. So it takes care of that negative part for us, right? And then from there, it's just like what we've been doing on the previous examples. Again, here we have, and just to reiterate, this becomes 1 over 2 because it's really 2 over 1. All whole numbers are over a denominator of 1 if we don't see something there. Here we do have a numerator and a denominator with a negative exponent, so we're going to find its reciprocal, which again just means flip it. And when we do that, it gets rid of the negative in our exponent, and we can go from there. So let's take a look at A together. So this is one that's a whole number, so remember that's the same as just being over 1. So then we can rewrite this as its reciprocal, 1 over 10. And now this negative 4 exponent is going to become a positive 4. And once we have that, then we know it's simply going to be 1 over 10 times itself 4 times, or just 1 to the 4th over 10 to the 4th. All right, another whole number one. 5 to the negative 6 is really 5 over 1 to the negative 6, which I can rewrite as its reciprocal, and that switches it back to a positive 6. Okay, so we're going to have 1 over 5 multiplied 6 times. So 1 to the 6 over 5 to the 6. And tomorrow we'll start simplifying these numbers, and I'll show you some stuff in the calculator, but for today, just leave them. All right, here's our first one that's not a whole number, right? It's 2 over 7. So whenever I'm trying to get rid of this negative exponent and I find the reciprocal, it simply becomes 7 over 2. And now we have a positive 3 exponent, right? And have you guys noticed the pattern here? Like, if I have a power of 4, basically both numbers just end up with that power. Same here, a power of 6. So the 1 and the 5 end up with a power of 6. So if it's okay with you, I'm just going to start going straight to that answer. So this will be 7 cubed over 2 cubed. All right, let's look at the next one. The reciprocal of 1/4 is 4 over 1 raised to the second power. Well, remember, whenever the 1 is in the denominator, we don't have to write it anymore, because 4 over 1, when we divide that, is just 4. So I can actually write this one without a fraction at all, as just 4 squared. All right, we're so close. All right, 9 to the negative 2. This is a whole number, so when I find its reciprocal, I'm simply putting a 1 over that number. Now it's to the positive 2, and so again, the top gets the power of 2, and so does the denominator, so we'll get 1 squared over 9 squared. Beautiful. another whole number. So that's really going to be the same as dividing by 8 5 times or multiplying by 1 over 8. So we're going to get 1 to the 5th over 8 to the 5th. And last but not least, 8/3. We need to therefore find the reciprocal, which is 3 over 8 to the positive 4. So we're going to get 3 to the 4 over 8 to the 4. And we are done. If you have any questions, make sure to let us know.